we're going to look at vertical circles. So after this, you're going to know a couple things, be able to solve for what's called the critical velocity, and solve tension problems for vertical circular motion. But before we do that, I'm going to answer a question that has plagued mankind for ages. You know the old loop-de-loop with the Hot Wheels track? Have you ever wondered if you could actually do that in a real car? So, you didn't have to write this down just yet. Consider a ball moving in a circular path as shown. What do the red and blue arrows represent in this little animation here? So, just let me see here. Where is the actual play? Is that it? Yeah. Okay, so what do the red and blue arrows represent in this little animation? What does the red arrow represent? Am I going to get anything out of you guys today? Notice, is the red arrow changing? The length is changing. So that means that it's a vector. Centripetal force, Connor, you're right. And you'll notice that, in fact, the centripetal force changes. When is it at its smallest? At the very top, right? And if you think about that, you've got my rubber stopper on a string here, right? And if I'm doing it vertically like this, if I go slow enough, what happens to the string at the top? It goes slack, right? Yeah. There's no tension at all in it. Is there some magical speed that I have to go? Like I can go faster and faster and faster, but is there some sort of smallest possible speed that will keep it in circular motion? And then after I go a little bit slower than that, then what happens? It falls apart, right? So is there some sort of magical smallest speed? The answer to that, of course, is yes. Okay? So the red arrow is tension. What do you think the blue arrow represents? What's it doing? Not changing, is it? Well, it's tiny. It's on the object. It is gravity, exactly, because the gravity on the object doesn't change as it goes around, right? Because gravity is just 9.8, right? Okay, now, what about the speed of the ball? What do you notice? A little harder to see on animation. Maybe I'll just do it in real life here. You can just imagine. Where is the speed at its fastest, Mark? On the down? On the down or at the bottom? Right at the very bottom. Why do you say that? Say that again? Gravity's helping it go down. So on the way down, gravity's pulling it down, and I guess you could argue on the way up, gravity's slowing it down. So, okay, by logic then, it's going as fast as at the bottom, you're saying, and would it be going as slow as at the top? Then you'd be absolutely right. Okay, so that's kind of the theory behind the sort of the what you need to intuitively know. Of course, we're going to get into the formulas right away, right? Here it is here in a little bit more sort of detail. You'll notice that the tension, the red arrow, I'm just going to make it a smidge bigger. You'll notice that the tension, the red arrow, is getting bigger and bigger and bigger. And the weight force is always pointing straight down, isn't it, right? Gravity's always pointing exactly straight down. And if I make it go faster, what happens to the value of the tension? It increases. In fact, there's quite a difference between the bottom tension and the top tension, right? And if I slow it down, oh, the tension almost goes to zero. What happens when the tension is zero at the top? Does it just fall straight down? It keeps going sideways, but it may not actually maintain that circular motion, right? The guy that was driving the car, he had to go fast enough that there was enough force at the top that he would stay in that circular path, but not so fast. Here, if you go too fast, what might happen? The string might break, right? But because he's going on the ramp, he's exerting an inertial force upward, a centrifugal force, if you will, on the ramp, and therefore the ramp, there's stress on the ramp, and they were worried that the ramp itself was going to collapse. So he had to nail that speed almost exact. What could they have done to make it more, what could they have done to the ramp so that he would go slower, or he would have to go slower? How could they adjust the ramp? It could, I suppose, that's right, but they would need to have some friction so that like it actually has a fraction to go. I guess, yeah. What about the size of the ramp? Would that change? Would that change anything? If it was smaller, Pauline, how fast would you have to go to maintain that circular motion? Would you have to go faster? Less fast, you think, if it was smaller? Let's just do this, make it a small circle. Wait. I think it's slower there, right? But maybe that difference between too fast and too slow might have been too much. Not really sure there. All right, here's where maybe you should start writing stuff down. I'll wait there for a second. I'm going to go do attendance. And you guys go ahead and jot that down, and then we're going to do the formula derivation and sort of the math behind it. All right, so because of gravity, the speed of the ball is not uniform. So I should I should say that when I say UCM, uniform circular motion, the uniform really stands for constant velocity. I say UCM in vertical, even though I know that the velocity of the speed is not uniform, okay? So if you see UCM in a vertical sense, I still mean the speed is changing. It's just, there's really no, I guess it's just circular motion, I guess, but we tend to use UCM. So where is it fastest? The answer is at the bottom. And where is it slowest? The answer is at the top. And if you keep that in mind in all the sort of problems that you're doing, okay, quite often, excuse me, we get issues with the positive and the negative signs and all that, and kids get a little bit mixed up. Always come back to where is it fastest, where is it slowest, and then you can make the math work. You can make the adjustments that you need to, or you can find the error that you've made. So what do these various things represent or mean? This V here, of course, stands for velocity. So at this point right here, the velocity is that way, and here the velocity is this way. It's going counterclockwise. Where's the acceleration, by the way? Which direction is the acceleration? Well, it's toward the center, right? And it's a centripetal acceleration. The acceleration and the force are in the same direction. Okay, so Fw and Fw down here stands for weight force. Because it's always down, here it's down, here it's also down, but you'll notice that here, Fs1 and Fs2 should maybe be Fs top and Fsb for top and bottom. Doesn't really matter how you label them. But that's the string force or the string tension at the top, and this would be the string force or the string tension at the bottom. You will notice that at the bottom, the string tension and the weight force are opposite to each other, and at the top, they are in the same direction. That's important as well. So at the top, how do you want me to do this? Do you want me to let you write it down and then explain it, or explain it and then let you write it down? Do you care? Okay, so at the top, FCT, the total centripetal force. Stay with me here, Sean. The total centripetal force, FCT, is the string force, FST, plus FW. This is FW, and this is the string force at the top. Right? And those two things combine together to give us the centripetal force at the top. Okay? And then the string force, this FCT, the centripetal force, as before, centripetal force is mv squared over r, and because we know that it's going the slowest at the top, we're going to call that mv min squared, the minimum velocity, the slowest possible speed. And that's equal to FST plus FW. And all of them are down. I'll pause for a second. So similarly, at the bottom, we've got this diagram, which is sort of just a zoomed in version of the one before. This is our weight force here, and this is our string force FSB, string force at the bottom. And the centripetal force total, FCB at the bottom, the centripetal force at the bottom is equal to the string force at the bottom plus the weight force. And again, that total centripetal force is mv squared over r. But because it's going the fastest possible speed at the bottom, we're going to label that mv max squared over r. And again, that's FSB plus FW. And here, note that the centripetal force and the tension are up, but the FW is down. Again, I'll pause. Maximum is bigger than minimum. Then the string force at the bottom, that should be this one here, this should be FSB, is greater than FST. The tension in the string, FSB, the bottom, is bigger than the string force, FST, at the top. The string tension is greater at the bottom. That's the other key thing to know. Goes slower at the top, faster at the bottom, less tension at the top, more tension at the bottom. And again, keep that in mind. All the other sort of mathematics you can adjust if you need to, because that will give you the answer. Use that for guidance, is what I'm saying. Okay, so the string tension is greater at the bottom. So this implies that there is some velocity below which the ball will not move in a circuit path, and the string will slacken at the ball's highest point. This could also happen if the car did not have enough speed to make the loop-de-loop, and I don't think I need to demonstrate, but that's what it could have looked like. That would have been bad for the dude, right? He wasn't going fast enough. You missed the video where the guy did it in real life there, Josh. So, how can I come up with some formula for this critical velocity? The minimum value is when the string tension is 0. When the tension in the string at the top is exactly 0, that's the slowest possible speed it can go. Okay? At this point, the ball just makes it around the circle. Just gets around it. One of these buttons slows it down. What's that? I don't know. Just when I embedded it in here, it didn't. Yeah, I don't know. Oh, maybe here? Oh, right here? I think that's the frame. Right here? Oh, yeah, no. Yeah, no, it's one of these here. But the diagrams have, I don't know. Anyways. So, at the top, and I got to fix this. I think I said it last year, right? FC1 at the top is equal to the FS string tension at the top. Just replace those ones with T's. Right? Centripetal force at the top is the string tension at the top plus the weight force. But at this critical velocity, that string tension is 0. Which means that the centripetal force, mv min squared over r, is equal to 0 plus mg. The 0 disappears. What else also disappears? The m's, and you're left with v min squared is over r is equal to g, which you can rearrange to this formula right here. I just derived a new formula. Let's call that v min. V min is equal to the square root of r times g. That's how fast the dude had to be going in the stunt car to make it all the way around. And if you actually went back and you look at the video, you can actually see that's what that professor was working out. You can see that formula. What do you notice that is not in the formula? I mean, there's lots of things that aren't in there, but what is there that you think might have been important that isn't? You may not notice it right away, and it'll be obvious once I tell you. No, not acceleration. What kind of car did they use? Pick a small car. Does the size of the car matter? What canceled on both sides? The mass. The mass of the car doesn't matter when you're going in that loop-de-loop. The mass of the car does not matter. So it didn't matter whether he was carrying gold bars in his pockets or helium balloons. The mass of the car doesn't matter. V min is equal to square root RG. Okay. This value of V min is called the critical velocity because it's critical that you go that speed. It depends only on the radius of the circle, and the acceleration due to gravity does not depend on the mass of the object in motion. Now, when NASA or other telecommunication companies put satellites in orbit, a satellite in orbit around a planet moves with a critical velocity for its radius of orbit or its altitude. What would happen if it moved faster? Like, if I go faster here, nothing happens. It just goes faster because it's attached by a string. What happens if the satellite's going faster? It's not going to maintain circular motion. In fact, it's going to like maybe create an ellipse, or it may actually escape, if it gets going fast enough, it may escape the planet's gravitational pull, which would not be good. What happens if it doesn't go fast enough? Here it just sort of collapses into not a circle, but if it's a satellite, what happens? Fall back to Earth, probably creating a bit of a problem. There'd be a disaster, a Michael Bay movie awaiting that to happen. Okay. Shall I do some sample questions? All right, so in this particular situation, we have a 0.5 kilogram body moving in UCM in a vertical circle. I mentioned it yesterday. Always identify what kind of circle it is. Is it a horizontal circle or is it a vertical circle? A radius 1.5 meters and period 0.5. Find the speed of the body in its orbit. Find the average centripetal force needed to maintain this motion. Find the string tension with the mass at the bottom, and find the string tension with the mass at the top, and find the critical velocity. Okay, so we've got our R is 1.5. Our period T is 0.5. And our mass, these are all 0.5s, our mass is 0.5 as well. And we are needed to find the average centripetal force needed. No, not the average centripetal force. First of all, find the speed of the body in its orbit. And in fact, that would be an average speed, wouldn't it? And so we're going to start with our sort of new friend here. V is equal to 2 pi r over t, which is really just a reworking of circumference, distance over time. 2 pi r, that's an r, not a v. 2 pi r over t. 2 pi. The radius here is 1.5. The period is 0.5. Telling us that the average speed has to be 18.8 meters per second. 18.8. And I guess we really should put a bar over that to indicate that it's an average. All right. So now, what is the average centripetal force needed to maintain this motion? Centripetal force, or Fc, is equal to mv squared over r. And there again, I slipped into the capital R. The mass, 0.5. The velocity is this new number, 18.8 squared, all over the radius, 1.5. Giving us 118 newtons of centripetal force. Okay? And this is the centripetal force. This is the net force. All of the forces on this object are combining together to give us the centripetal force. Now, when this is at the bottom, part C, when we're at the bottom, right, you've got the tension up, and you've got the weight force down. Those two together add up to create that centripetal force, right? So the tension, in fact, does it have to be more than 118? It's kind of like, you know, if you need 100 newtons of net force, and you got 20 newtons of friction, how much do you have to push? 120. Right? The FW here kind of acts like a brake. It kind of is a kind of like friction against the tension, right? Okay, so this F net, I'm going to write, and this is always a little bit challenging here. F net is going to be the I called it tension there, didn't I? Tension, or FT, or FS1, or whatever you want to call it, plus the weight force. And this F net is. Now, here's where the direction matters. The F net, the 118, at the bottom is in what direction? Up, which is positive. So this is going to be positive 118. The tension is what we're solving for, but the weight force is which direction? Down. So minus m times g. So this is going to be minus 0.5 times 9.8. So in other words, I got 118. I'm going to take that 0.5 times 9.8. That's going to give me minus 4.9. And then that's going to become plus 4.9 over here. And my tension is 118 plus 4.9, or 122.9 newtons. Is my tension more at the bottom? Yes, I'm good. What kind of number am I going to get for tension at the top? It's going to be less than what, Connor? Less than 122.9 or less than 118? It will be less than 122.9, but it will also be less than 118. Okay? Do you want to try that on your own, or do you want me to show it? No response, I will just go ahead and do it, I guess. It's like everyone is sleeping. Maybe I should have recommended the Monday size coffees today. At the top, tension is down. Weight force also down, right? F net is equal to tension plus weight force. The only thing that changes here, that differs, is the direction. And that net force, that 118 of centripetal force, is now what direction? It's down. We're solving for tension again. Which way is the weight force? Same as before, minus 0.5 times 9.8. The only difference is that minus, the 118 is negative over there. So now I'm going to get minus 4.9 there. And then when it goes to the other side, my tension is positive 4.9 minus 118. And our tension is only minus 113.1. Less than 118. Why less? Why is there less tension in the string? Because what's helping at the top? Gravity. Gravity is providing a force that's also causing the rubber stopper to fall as it goes. I don't need as much string force. Gravity's helping. At the bottom, gravity is actually working against the string, right? So keep that in mind. At the top, it's going to be less, minus 113. At the bottom, it's going to be more. And if you do that, you should be fine. I think there's one more question, right? Doesn't it ask for the critical velocity? And that one is probably the easiest one. The formula was V min is the square root of R times G. Radius, I gotta look back, 1.5. Should I put negative 9.8 in there? Well, it actually does matter. Most of the time it doesn't, Connor, but in this case it does. Why? And not because there's any direction, it's because when you put that negative in there, you're going to get a negative inside the square root, and you're not going to be able to take the square root of it. Okay? Is that what you were thinking? Yeah. So it doesn't matter in that there's no directional component here, because the velocity is, right? It's a circular velocity, but because of the nature of the formula, we're going to have to leave it as positive. So I get 3.83 is the critical velocity. Okay, I think in the interest of the fact that we're missing a few people, and we're doing okay for time, I think I will give you the rest of this period. It's not a whole lot, and I'm going to do, there's a second sample question here. I'm going to do that one as sort of as a reminder, sort of an intro tomorrow, and then I'll probably give you some time to work tomorrow as well. And we'll leave the flying pig, today's Wednesday, right? We'll leave the flying pig for Friday. That'll be an exciting Friday event. And then we are looking at, let me just look ahead here. We got to look at bank curves on Monday, probably another day of review on Tuesday. So we're probably looking at a test roughly about Wednesday or so next week. Anything going on in the next? So roughly Wednesday or Thursday of next week, we'll have the next test. There's a couple of instances in that worksheet where it talks about the G's, so you have to be able to convert from G's to acceleration by using that 9.8.